Hi students, in this video I will go through the derivation for why the centroid is in fact the center of mass of a triangle. This derivation, it's more like a reasoning or proof of why the centroid is the center of mass. And I'd like to preface this this proof or this derivation by first establishing maybe perhaps some foundational things to to which we can work with. Okay, and that is the we're starting off with having an understanding that the centroid is formed by the intersection of medians. Okay, so this point, hold on a second. So this point right here, okay, is our centroid. And if we were to cut this triangle out and place this triangle on a pin at that point, the triangle would be able to balance itself. Okay, that's what it means for something to be the center of mass. Okay, so that point is in fact the center of mass. That's what we're trying to prove. Okay, and the way in which we're going to try to prove this is we're going to equate, and I'm not saying that that mass is equivalent to area, okay? But that's what we're going to sort of establish as the ground rule. That area, we're going to equate area with mass. And those who have gone through any basic science class, okay, will understand that mass, okay, is like the substance, for an object. So we're going to equate, okay, the area of the triangle to mass. All right. So very similar to the last video that I made regarding like the derivation or the proof of why the centroid breaks up, or why the centroid is 1/3 away from any vertex, or 2/3 away from any vertex and 1/3 away from any base. I'm gonna go through this thought experiment with you guys, okay, to show why the centroid is in fact the center of mass. And the way in which I'm going to do this, okay, I'm not going to I'm not going to place the triangle on a coordinate grid. This time, just like with the last video, we want to like eliminate as much variation as possible, right? So again, I'm not saying that my approach here is like the way, but this is just a way that I thought of it. Perhaps there are more efficient ways, okay, in which you can probably Google and get a more efficient way. But this is the way that I had approached it, okay? People have said in the past that math is not creative. Well, this is an example of why math can be very creative, okay? And this is the way in which I'm approaching this, okay? So the way in which I'm going to approach this is because I'm working with area of the triangle, I'm going to subdivide that triangle into 6 regions, okay? And if the centroid is in fact the center of mass, then my ultimate goal would therefore be to show that all the areas A1 through A6 here must be the same. And also be aware of this, okay? I've also labeled, okay, these side lengths as X's and Y's and Z's, okay? I'm not saying that I know what X, Y, and Z is, but what I'm saying is, okay, that the medians, okay, they're breaking up the 3 side lengths, okay? They're bisecting it, okay? So all 3 side lengths do not need to be the same. All 3 side lengths could be the same, okay? It doesn't matter, okay? But our ultimate goal is to show that A1 through A6, all those areas are in fact the same. And how am I going to do that? Well, the way in which I devised it, or at least the method that I thought of, okay, that would be most appropriate, was to somehow show that A1 and A2, I'm going to start off with that, okay, that those 2 areas are the same. Now, unfortunately, okay, I will need to introduce another variable here, okay, but this variable is going to help us. It's going to be our quote-unquote dummy variable, okay? If we rely on the formula area is equal to 1/2 base times height, then I can then establish that A1 must equal to, that the area for A1 must equal to 1/2 times h sub x times x, right? Lowercase h sub x times x, because the height of the triangle is h sub x, which I don't know what it is, but I'm just going to call it h sub x. And the base of triangle A1 is just x, has a length x. So that's the area for A1. And wait a minute. Isn't that also the same as the area for A2? Right? The base of the triangle has a length of x. The height of the second triangle also has a height of h sub x. So therefore, just very intuitively, okay, we've already established that the two triangles, A1 and A2, will have, in fact, the same area, which was my goal, to start with. My goal was to show that A1 through A6 have the same area, okay? So with that said, okay, I am now going to, instead of showing A1 and A2 having the same area, I will now do the same thing with A3 and A4. And notice that the triangles are in the same orientations. So if you take a look at this A3 and A4, it's right here. Notice that A3 is in the same exact orientation, right? And then A4 is right over here. And notice A4 is in the same exact orientation. So again, I'm trying to show that A3 and A4 have the same area. And again, I'm going to use that dummy variable, h sub y. Ultimately, at the end, we don't really care for what h sub y is, okay? But the whole point of this is to show that both triangles having the same base length of y and having both the same height, h sub y, will therefore have the same area. So therefore, a sub 3 and a sub 4 must be the same. I will repeat this one more time to establish that 5 and 6 will be the same. So again, I am going to, in the same orientation, draw out triangles 5 and 6. So triangle 5 is right here. Notice that it's in the same orientation, it's in that same pitch. And triangle A6 is right here. Notice that it too is in the same pitch. Okay, and again, using the same technique, I can therefore also show that A5 and A6 are the same. So this is what I have right now, just to summarize. Okay, I've established that A1 is equal to A2, A3 is equal to A4, and A5 is equal to A6. My next goal for the next couple minutes is to somehow link A2 with A3 and perhaps A4 with A5, that those are the same. Now, how am I going to do that? I'm going to have to broaden my division of areas, okay? So I can do what I just did here in this first column, right? But instead of just focusing on A1 and A2, I'm going to focus my attention on 3 sets of areas this time. I am going to devote my attention to, I'm going to erase this, and I'm going to erase this. I'm going to devote my attention to, I'm going to erase this, and this, and this. I'm going to devote my attention to this left half, because this is one giant triangle, also sharing base of x, and then this triangle on the right. So I'm looking at the left half and the right half. So if I do that, let's take a look. I have this. So again, with the same process, okay, now I'm dealing with a larger triangle comprising of 3 smaller subdivisions, okay? And I'm going to call the height of this bigger triangle capital H of x. And again, it really doesn't matter what capital H of x is. The whole point of this is to show that capital H of x is being shared between the left half of that triangle and the right half of that triangle. Both triangles, both of these bigger subdivisions of triangles, okay, are sharing the same height, capital H sub x. And if I do this, okay, you're going to see that 1/2 capital H of sub x times x is going to be equivalent to 1/2 capital H sub x times x. The next part here is a little different from what I did in the last like 2 minutes, and that is 1/2 capital H sub x, okay, this left triangle here. Wait, isn't that area A1 plus A5 plus A6? And the right half of the triangle, isn't that just A1 plus A2 plus A3? I'm sorry, A2 plus A3 plus A4. Okay, so that's what I'm going to do. This is my bridge, okay, this is the bridge between these two, okay? That's how I'm going to link A2 with A3 and A4 with A5 and so forth, okay? So I'm going to repeat this one more time, and this time I'm going to find I'm going to try to do the same thing, but I'm going to do it with the top half involving y and the bottom half involving y. These two triangles. And if I do that, let's take a look at the breakup. I have this. So the area of the top half and the area of the bottom half, okay, we can find out what they are very similarly, okay, using that same approach that I just did a moment ago. And again, I can then conclude that the area of the top half and the area of the right half is actually going to be equivalent. A4, A5 plus A6 will equal to A1 plus A2 plus A3. And then the last thing I'm going to do, okay, is to show that, that the area of the triangle with base Z is going to be equivalent. Well, the left half and the right half are going to be the same, or the top half and the bottom half are going to be the same. So let's take a look. If I do that, I break up the triangle into those two, right? And again, I can see very clearly that both triangles will share H sub Z, and using a very similar technique, it can be shown that A1 plus A2 plus A6 is going to be equivalent to A2 plus A4 plus A5. If you want to pause a video at this moment, okay, and just maybe think about algebraically how am I going to, or how are we going to figure out that A1 through A6 are all in fact the same, I'd encourage you to, try this on your own. Otherwise, keep on watching the video. But again, at this moment right now, I have 6 different relationships. I have 6 unknowns, right? A1 through A6. This is enough. There is enough relationships right now for me to make some conclusions about the relationships between area 1 through area 6. What we're going to do, because we have 6 unknowns and 6 different equations, we can once again fall back on the concepts that we had studied in Algebra 1, which is systems of equations. So what I want to do is I want to take this first row right here, A1, A6, A5 equal to A2 plus A3, A4, and I'm recognizing that A1 is equal to A2, we can then perform a substitution. Or actually not a substitution, but we can perform a subtraction, right? We can eliminate some variables and therefore conclude by subtracting both sides with A1 A2 equal to A2, we can then conclude that A5 plus A6 is equal to A3 plus A4. And subsequently, we can do this for the other 2 sets of triangles, right? I can do the same thing with these. and this. And I can make very similar conclusions. Okay, and that is exactly what I'm going to do. I am going to perform subtraction. And if I do that, this is the relationship that I end up with. I end up with A5 plus A6 is equal to A1 plus A2. And then the last one, I'll end up with A1 plus A2 is equal to A3 plus A4. So I am slowly whittling away, okay, at the number of unknowns that I have. At this stage, okay, now I have A5 plus A6 is equal to A3 plus A4. I can begin to whittle away some more. Okay, so again, we established this in the last step. We also established in the previous steps that A5 was equal to A6 and that A3 was equal to A4. So because of this, I can make a direct substitution. Instead of writing A5 plus A6, I can write A6 plus A6 will equal to A4 plus A4. So therefore, I have 2A6 is equal to 2A4. Or, consequently, this is my first connection, that A6 is equal to A4. And since A6 is equal to A4, and A3 is equal to A4, right? And A6 is equal to, and A4 is equal, A3 is equal to A4, and A5 is equal to A6, we can then conclude that all those things are the same. A3 is equal to A4, which is equal to A5, which is equal to A6. Last, I'm going to take this relationship, which we had solved down here. Remember that? This guy? A1 plus A2 is equal to A3 plus A4. And I'm going to make another substitution, which was A1 is equal to A2 and A3 is equal to A4. And in a very similar manner, make the correct substitution. And then conclude that A2 will equal to A4. And this is my final link. If A2 is equal to A4 and A1 is equal to A2, we can then conclude that A1 is equal to A2, which is equal to A3, which is equal to A4. And then the very last step, since all these things are equal to one another, this is the last connection that we have to make, which was A1 is equal to A2, which is equal to A3, which is equal to A4, which is equal to A5, which is equal to A6. So what does this mean? This last rectangle that I drew, that I wrote down here, this is saying that surrounding the centroid, surrounding that center of mass, okay, it is fitting to call that point the center of mass, because all the areas, all the quote-unquote mass of the triangle, all surrounding that point, they are in fact the same. Which is why in geometry we put so much emphasis in the study of centroids. Anyway, there's a document that goes along with this, okay, where you can like zoom in on the various parts of this of the computation work that I have done here. But otherwise, I would recommend like maybe perhaps rewatching this if it didn't click at first. And definitely come to office hours if you have any questions regarding anything that I've said today in this video. Talk to you guys later.